Students and general seekers of truth. In this video, we are going to find the derivative of this particular function, f of x equals x to the 10th, and also expand on this idea, and we'll kind of see where calculus and discrete mathematics intersect. So let's begin. We know that the derivative formula, or the derivative definition, using the difference quotient is a limit as h approaches 0 of f of x plus h minus f of x all of it over h. Now, when we go and apply this definition to the particular function, we get the limit as h approaches 0 of x plus h to the 10th power minus x to the 10th, and all of this over h. And of course, we can expand that x plus h binomial, this term right here, and we're going to get something pretty gnarly and complicated. But we can sort of at least see a few of these terms, and then anticipate and see what the pattern really is to it, just to avoid the tediousness of it. So we know that x plus h to the 10th using the binomial theorem. All right, so that's very important. If you don't know what the binomial theorem is, please look it up and watch the previous video. So binomial tells us that we're going to have 10 choose 0 times x to the 10th h to the 0 plus 10 choose 1 x to the 9th h to the first power plus dot dot dot. We're going to continue that pattern until we get to the last couple of terms here. This is going to be 10 choose 9. It will be x to the first h to the 9 plus 10 choose 10. Should I 10 choose 10 x to the 0 h to the 10th. And then, of course, we still have that last term minus x to the 10th there. And all of this over h. Now, I don't know exactly what all the numbers are for 10 choose 2, 10 choose 3, and so on, but I do know a few things. That 10 choose 0 is just 1, so that gives me x to the 10th. 10 choose 1 is just 10, so that gives me 10x to the 9th h plus a lot of terms in here. Don't quite know what all of them are until I get to the end here. 10 choose 9 once again is 10x h to the 9th. 10 choose 10 is just 1 plus h. So 10 choose 10 is just 1 to the 10th. And then we still have this minus x to the 10th right here at the end. So all of this, and we take the limit as h approaches 0. Well, some nice things happen here. X to the 10 and negative x to the 10 cancel. And really, that's about all that we can do. Unless you consider the fact that every single one of these terms here has an h in it. There's an h here, there's an h here, there's an h here, and there's an h in all of these terms. All of these terms in the dot 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 here also has an h. So what we can do then is just factor out that h. And let me show you what I mean. So we continue over here. Let's factor out that h. Still have the limit here as h approaches 0. All of this is over h. But in the numerator, we can factor out an h. And what do we have left? Well, we have 10x to the 9th plus all these terms here, they all have an h in them, plus the last couple of terms. This would be 10x h to the 8th plus h to the 10th, but we already factored out 1h, so we're going to have h to the 9th. And because we factor on h, we can eliminate those h's, they cancel each other out. And then we can continue here, and now we can use direct substitution. Excuse me, we don't need the limit anymore. If we in fact perform direct substitution and we plug in 0 for h, keep in mind this term in here has h's in them, these terms in here have h's in them, this term has an h in them. So we plug 0 in for everything, all of it goes away, all of it cancels out, and we end up with simply 10x to the 9th. So the derivative of f of x equals x to the 10th is 10x to the 9th power. And you can see there how the binomial theorem comes through for us big time. Not because it does anything special, other than giving us a quick systematic way to evaluate every single term. We could also evaluate this manually just by multiplying everything out 10 times, but that would be extremely tedious. So I'm going to end this video here, and I will start another video where we look at the general case and we see the true power of the binomial theorem. Thank you for watching, and have a wonderful day.